For this problem, I will be using the general rate equation to solve for values of p, q, and k in an equation. The general equation for this can be represented by a plus b yields c plus d. The dependence of this rate concentration can also be used with the equation rate equals k times the concentration of a to the p times the concentration of b to the q. For this problem, I will be using the following equation. I will also be using the standard rate law equation, which is d times the concentration of d over dt. In this case, d times the concentration of d equals the change of the concentration, and d times t equals the change times time. I will also be using this following table to obtain values to solve for p, q, and k. First, I will be solving for the value of p. In trial 2, the concentration of NO was doubled from that in trial 1. While the concentration of H2 remained constant, doubling the concentration of NO increased the rate by a factor of 4. I got the value of 4 by dividing 0.096 by 0.024. I retrieved these values from the table in the previous slide. Since 2 to the p must equal 4, we can assume that p equals 2 because 2 squared also equals 4. In the same way that I solve for p, I will solve for q. In trial 3, the concentration of H2 was doubled from that in trial 2, while the concentration of NO remained constant. Doubling the concentration of H2 increased the rate by a factor of 2. I got 2 by dividing the trial 3 value of 0.19 by the trial 2 value of 0.096. Since 2 to the q equals 2, q must equal 1 since 2 to the 1 equals 2. Now that we know the values of p and q, we can plug these values back into the original equation and solve for k. .024 equals k times 0.2 squared times 0.1. Now, divide 0.2 squared times 0.1 on both sides, and doing this you will get a value of 6 for k. Now you can rewrite your final answer as follows. D times the concentration of N2 over D times T equals 6 times the concentration of NO2 squared times the concentration of H2.